This morning I want to talk about the Fiat-Shamir Transform. Very, very exciting idea from the 80s that I personally and many other researchers in the area find really intriguing. Okay, so what is the Fiat-Shamir Transform? First of all, it was proposed by Amos Fiat and Adi Shamir back in '86. And we'll see what it is in great detail. But in a nutshell, it's this really incredible idea of reducing or even, in some sense, removing interaction from interactive protocols. And this idea has been extremely influential, both in theory and in practice, which is something that I find pretty unique and nice. And let me just mention that the view that I'm going to present today is kind of a more modern view of this transform. Originally, the way that Amos and Adi proposed it was as an idea for transforming something called an ID scheme, something that Alon talked about yesterday, which is something that is relatively easy to construct. So the idea was to transform an ID scheme into a signature scheme, which is something that, on the face of it, looks much more fancy. Okay, but we're going to take a kind of a much more general view of the Fiat-Shamir transform today. So before telling you what it is, let me briefly remind you what an interactive argument is. So notion proposed by Brassard, Chalman, Cropot in '88. So it's very similar to an interactive proof. So we have a verifier V and a prover P. The prover is trying to convince the verifier that an input X belongs to the language L. So they interact, send messages back and forth. We have the standard completeness requirement. That means that P convinces V to accept the probability, let's say 1 or close to 1. And soundness, or rather computational soundness, says that a computationally bounded cheating prover, so say a polynomial time cheating prover, cannot convince the verifier to accept the probability that is non-negligible, to accept a false input, X that's not in the language L. An important definition that we're going to need in this talk today is the notion of a public coin proof or public coin argument, which simply says that all the messages sent from the verifier are just uniform random strings that he just, the way that protocol works is the prover sends a message, verifier tosses some coins, sends the coin. Prover sends another message, verifier tosses more coins, sends the results. All the messages are very, very simple, just uniform random coin tosses. And that's going to be important. Okay, so with that in mind, we can define the Fiat-Shamir transform. And remember, the idea is to take kind of an arbitrary public coin interactive argument and generically transform it into a non-interactive argument, meaning a single message sent from the prover to the verifier, kind of our dream version of an interactive proof. Okay, so we have on the left this interactive argument between P and V. And we want to kind of squish a number of rounds. And it seems kind of difficult to do. Right, and we're going to denote the messages from the prover to the verifier by alphas, and the messages from the verifier to the prover, these random coin tosses by beta. And we want to kind of squish this interaction. And the key idea of Fiat and Shamir is to use some incredibly complex or elaborate hash function. I'm not going to state yet what, or probably not in this talk, what properties this hash function should have, but let's just think of it as being really, really complicated for now. Okay, so we have this hash function that we can use, and here's what our new prover, PFS, is going to do. So, he's trying to mimic the prover on the left. What can he do? First of all, he generates the message alpha1. But now, where's he going to get beta 1 from? We can't afford for the new verifier to send anything because we don't want interaction. And the idea will be that we can obtain beta 1 by simply hashing alpha 1. And for good measure, let's throw X in there too. And kind of the key idea is that if H is so elaborate and complicated, then somehow beta 1 is unpredictable. And we've gotten kind of a fresh beta 1, which is essentially as good as one that the verifier would have sent us. So the prover got beta 1, and if things sound vague, then they should be, so don't worry about it for now. He got beta 1. Given beta 1, he can now produce alpha 2, kind of continue the interaction. Now to get beta 2, he simply hashes kind of the transcript so far, so alpha 1 and alpha 2, gets beta 2, and now we can compute alpha 3, send that, and all of these are going to be sent in a single message, and proceed generating all the betas as hashes of the alphas, eventually the prover has all of these messages, alpha 1 up to the last message, alpha r, and sends them to the verifier. And that's that. And so that is basically the Fiat-Shamir Transform. And we're going to talk about that kind of in detail today. So first of all, that kind of something that I already mentioned, it's an extremely influential methodology. The reason for that is, A, because it's extremely powerful. We kind of know that interaction buys you a lot, and Fiat-Shamir come along and say, you know, this interaction is coming for free. So anything you can do with interaction, Fiat-Shamir say, you know what, you can do this non-interactively. So it's pretty amazing. Second is that it's essentially very practical. All we need is kind of this basic hash function. We didn't say what properties it has, but let's say we just use AES or something, so it certainly seems practical and in fact is being used. And it has a lot of expressive power. Because it's so generic, it talks about kind of general protocols. You can get things like, you know, the original motivation, which was efficient signatures, something called CS proofs, related things such as snarks, darks, and so forth, which are actually being developed nowadays, and there's great progress in the area. So extremely influential and important methodology. The question is it secure, right? We have this idea, we have this kind of vague, or we have this hash function, we don't really know what properties we want. Is it actually secure? And this is, I think, a really central question in cryptography, right? So do there exist hash functions for which this transform is secure? This is something that we'd really like to understand. And we do have some understanding, but it's far from complete, and it's a very active area of research. But nevertheless, something that we have known for a while, and I want to show you today, is that kind of in the best case scenario, when the hash function is kind of the best hash function, then we'll show that it is secure. What is the best hash function? Essentially, or ideal hash function. So that's going to be a totally random function. And I want to define that more precisely. And to do that, we're going to use something that's called the random oracle methodology, proposed by Belar and Ragoway. And the idea, so it's going to be the focus of the talk now, but it's also used outside of the context of Fiat-Shamir, so another very influential idea. So what is the random oracle model? So it's a pretty basic idea. We simply say we're going to choose a totally random function, let's say from 0, 1 to the lambda is the security parameter, to 0, 1, or to 0, 1 to the lambda, doesn't really matter. Just think of this kind of as an exponentially long string or truth table that all the parties can access. So all the parties that we have in the protocol, both honest and dishonest, can make queries to this totally random function and get back the answer. So if you query point x, you get a totally random answer. If you query a different point, you get an independent and fresh answer to the new point. Of course, if you query points that you already queried, you get consistent answers. Okay. And when we define security in the random oracle model, we will just require security to hold with high probability over a choice of the random oracle. So definitions of, say, completeness, soundness, and zero knowledge is a bit more tricky, should just hold with high probability over a choice of the random oracle. And there's a question of how should we view protocols that are proved to be secure in this random oracle model. And it's kind of a philosophical question that I don't want to address now. We'll get back to that later. Okay, but this is the random oracle model, and this is what we're going to consider, right? So we want to think of our hash function for the Fiat-Shamir transform as being a random oracle, accessible to the verifier and the prover, and potentially to a cheating prover. So totally random function R. And now when we hash our messages, we're going to use this totally random function, which seems kind of intuitively like a good idea because we hash alpha 1, we get kind of a random fresh beta 1, which kind of sounds like what the verifier sends in the protocol on the left. So it sounds promising. So here's the theorem shown by Poincheval and Stearns. Actually, they were talking about signatures. The extension that I wrote down here, I don't believe it's, to the best of my knowledge, it hasn't appeared in anything written, but it's kind of folklore. So the claim says that if you take any constant round interactive argument pi that has negligible soundness, and you compile it in the way that we saw in the previous slide on the right. So I'm going to call this new protocol pi sub fs, or rather pi sub r here. So that protocol is going to be secure. Security is talking about is a little bit vague. I'm talking about somehow both soundness and zero knowledge, with the focus being on soundness. So is the theorem clear? So you take any constant round argument that you like, and you can squish it down in the random oracle model using the Fiat-Shamir transform. And I'm going to show you how we do this. Sorry, any constant round. Sorry? Why did you need constant round? So great, so tightness. So thanks. So that's exactly, before going into why it works, I want to show you why you can't extend it beyond constant round. So I want to show you that there exists a protocol that has more than constant number of rounds, that has negligible soundness, like we wanted, but the compiled protocol is going to be not going to be sound. Okay, so I hope that answers your question. And it's not going to be sound even if we use this ideal hash function. So what's the idea? So in a nutshell, what we're going to do is take an arbitrary constant round interactive proof that has constant soundness, not negligible soundness, constant, and repeat it sequentially. So let's see what happens when we do that. So here, I'm going to think of starting off with a protocol. Let's say I start off with a protocol with just 2 messages. So the first one sent from the prover to the verifier, and then the verifier tosses some coins and decides. And let's say that that protocol had constant soundness. And now I'm repeating it sequentially, right? So the first 2 messages are just the first iteration of the basic protocol that we have with constant soundness, and so forth. And repeating it sequentially, we know by the fact that sequential repetition of arguments reduces soundness error at an exponential rate, we know that this is going to have negligible soundness, rather negligible soundness error. Okay? But what about the protocol on the right? And let's imagine here h can be anything. A concrete hash function, random oracle doesn't really matter. This is how we compile the protocol, and I claim that it's not sound. And what's the reason? Well, here's my cheating prover strategy. I'm going to choose somehow alpha1 at random, hash alpha1, and I get beta1. Now I know because the protocol, the original protocol that I started off with, only had constant soundness, I have some constant probability that kind of beta1 is good for me. If it's not good for me, I'm going to discard it and choose a fresh alpha1. I'll repeat it, an expectation, a constant number of times, and I'll end up with a beta1, which is good for me as a cheating prover. Once I get such a beta1, I can proceed. Now I'll choose alpha2, a constant number of times, until beta2 is something that's good for me. And I can go on like this to eventually get basically win here with probability close to 1, or 1 maybe in expected time, expected polynomial time. So I hope that answers the question. This is an example of a protocol with a super constant number of rounds, negligible soundness error on the left. But after you compile it, it becomes totally insecure no matter what hash function you use. By the way, this is something that I think many people in our community are not aware of, and there are papers that apply Fiat-Shamir to multi-round protocols without arguing why it should be sound. So it's something I think it's good for people to know. Is the concern just that if alpha2 comes from a small domain, then maybe I won't hit beta2? So I get to choose the original constant round protocol. So let's think of having very long prover messages.
You mean entropy also? It's not how long it is. I should have many possible options.
Right, if it's long, but I'm a cheating prover. I can choose, if the message is allowed to be long, I can choose whatever message I like. As long as,
it has to be consistent with the protocol.
Right. So the think of the protocol in which the verifier ignores alpha. Yeah. More questions?
Why can't the cheating prover do that for the constant?
So we're going to see a proof, but so the question was right. So here I'm leveraging the fact that the basic protocol I started off with had constant soundness, and that meant that in each iteration I only needed a constant number of times to hit a good beta. If I had negligible soundness, then I would need a super polynomial number of times to hit a good beta. Okay? Right, and in fact, so this is the theorem that we just saw. This is what Moore is saying. So there are extensions of this. If you're interested in references, then I'm happy to tell you offline. Extending it to some classes of multi-round protocols. Maybe most importantly, take any protocol that you like, apply parallel repetition. That protocol is going to be, you can apply Fiat-Shamir securely to that protocol, certainly in the random oracle model. Okay? So it's not kind of a, nevertheless, I wanted the theorem statement to be precise here and to explain why we need this restriction on constant round and the negligible soundness error. Okay, so I want to show you the proof of the theorem in kind of detail, but to kind of help both me and you, let's focus on the case of just a three-message protocol. Right, so we start off on the left with a three-message protocol. The prover sends alpha, verifier sends random, coin tosses beta, and then the prover sends gamma. And we compile it using the random oracle. So the prover generates, the prover generates alpha, computes beta as the hash, and then generates gamma as in the protocol on the left. And I want to show you that this transform is going to be secure in the random oracle model. Okay, so to argue that it works, I need to show you kind of completeness, soundness, and zero knowledge. Let's kind of go back and stare at the protocol. So completeness should be more or less immediate. Let's imagine that the protocol on the left had perfect completeness. Then it doesn't really matter what choice of random oracle you have. For every message beta, the prover can generate a gamma that will make the verifier accept. Okay, so completeness is easy to argue. It's also easy to extend to imperfect completeness. So completeness is fine. Really, the challenge is in proving soundness. So, we're going to do it by reduction. So let's assume that there exists some x that's not in the language, a false input, and some cheating prover for the compiled protocol. Let's say the prover runs in some polynomial time t, and it makes our Fiat-Shamir verifier accept with some noticeable probability epsilon. Okay? Given such a prover, we're going to construct a cheating prover for the original interactive protocol that makes the verifier there accept with probability that's kind of polynomial in epsilon and in 1 over t, which in our setting is going to be polynomial, which is a contradiction because we assumed the protocol had negligible soundness. Okay, so far? Okay, so to do that, we're going to, not going to be terribly complicated, but to do that, we're going to use kind of a little bit of probability. In particular, this kind of useful fact, which is something that maybe some of you have seen, but I want to be, to address also people who haven't seen it. So kind of very just generic and simple probabilistic statement saying the following. Suppose that we have kind of a joint distribution between random variables x and y, and there's some event happening over this probability space, an event A. And let's say that this, if you sample kind of x and y jointly, the probability that A happens is at least epsilon. Then what the fact states, if this is true, if over a random sample of x and y, the event happens with probability epsilon, then there is some kind of non-trivial fraction of x's in the world, or in this probability space, so that the version of the event where we fix kind of, so there is a non-trivial fraction of little x's, so that the event A relative to this kind of fixed little x, and a random sample of y conditioned on little x still happens with non-trivial probability. Okay, so kind of a nice fraction or good so fraction here essentially means good probability over a choice of little x from big X. So with epsilon over 2 probability of a choice of little x from big X, the probability over y conditioned on little x of this event happening is epsilon over 2. And I hope it wasn't too vague. It's going to be easy to prove. So the proof is essentially Markov's inequality. So that's kind of, again, for people who have seen it, maybe it's just a reminder. Because Markov's inequality is a one-liner, I'm going to show the proof in more detail also. So suppose that the claim does not hold for contradiction. And let's define x, little x, to be good if this equation holds. Okay? And we're assuming contradiction, so we're assuming that for less than epsilon over 2 fraction of the x's are good. And now let's consider our kind of original event, a of xy. So by just elementary probability, the probability of this event is equal to the probability that x is good times the probability of the event conditioned on x being good, plus the probability of x being bad or not good, times the probability of the event happening conditioned on x being bad. Okay, why did I do that? Well, if you look at over here, the probability of x being good by our assumption, the assumption that we just made, is at most epsilon over 2. So I can bound that by epsilon over 2. And this is a probability of some event. It's at most 1. So I have the 1 over here. And then for the second operand, we have the probability of x being bad. Can't really control that too much, so I'm just going to put a 1 over here. But now the probability of a of xy happening conditioned on x being bad is kind of, so if x is bad, it means that this equation does not hold. And therefore, we have epsilon over 2. So overall, we have epsilon over 2 plus epsilon over 2, which is epsilon. We got that the probability of the event happening is less than epsilon in contradiction to our assumption on the event. Okay. So kind of a slight detour to probability theory, but this is going to be kind of the heart of the matter. So going back to Fiat-Shamir, we've assumed that we have a cheating prover that breaks soundness of the compiled protocol. We want to construct a prover for our original interactive argument. Okay, so let's kind of try to analyze soundness, and we're going to look at what exactly this cheating prover for the Fiat-Shamir protocol does. And to do that, I'm going to, so just some notation, this prover runs in time t, and this time can essentially make at most t oracle queries to our random oracles. And I want to think of these as random variables, and I'll denote them by q1 up to qt. And without loss of generality, I want to assume that all of these QIs are both distinct, and that alpha, the message, the kind of first message that the prover sends, the cheating prover sends in the protocol, is contained in one of these queries. And how do I justify this assumption? Well, for the QIs to be distinct, that's kind of an easy assumption. I can just assume that the prover keeps track of all the queries that it makes, and if it ever wants to make the same query again, it just looks in its kind of in its memory and sees that it already made the query. So that's easy. And what about the assumption that alpha is contained in the list of queries? Well, first of all, it kind of doesn't make sense that it wouldn't, because it's trying to guess beta. But just to justify this assumption, just think that at the very end of the protocol, if it hasn't already queried on the point alpha, it makes another query. Okay? So I'm going to make these assumptions about the QIs. Now, what I claim is that there exists some I star, some particular index among these queries. So we already know that the prover wins with probability epsilon. I claim that there has to exist an I star so that the prover wins with probability at least epsilon over 2, so a little bit of a loss, but now it's conditioned on the I star query being alpha, the message that it's going to send as its first message to the verifier. Okay, and the reason for that, we can claim, say it's a hybrid argument or whatever, but for me it's easiest to think of it, suppose that it doesn't hold, then, you think of the entire probability space, different choices of I star, you're covering the entire, so you divide the probability space, partition the probability space into t parts, each of one has kind of measure less than epsilon over t, overall you're going to get less than epsilon probability. So I hope this is easy to see. And this claim is going to be useful. Okay, so kind of going to the heart of the matter, it's something called the Forking Lemma. The motivation for the name somehow comes from the original paper of Ponchev von Stearns, which kind of focuses on signatures or applications of this idea to something called Sigma protocols, which Benny will talk about later today. But let's kind of not focus on the name, but rather on the essence. So what is this lemma saying? So the claim is that for an epsilon over 2t fraction of q1 up to qi star, remember I star is this particular query in which we ask about alpha. And here, when I'm talking about fraction, I simply mean probability over the choice of, so with good probability over the choice of q1 up to qi star, so epsilon over 2t probability. It holds that the cheating prover wins with probability epsilon over 2t, conditioned on both the I star query being alpha and the first I star queries being exactly q1 up to qi star. Okay? So again, I'm saying that with good probability over the choice of the first I queries, the probability over all remaining coin tosses of kind of the prover convincing the verifier to accept is still, so with epsilon over 2t probability over the first part, you still have epsilon over 2t probability over the second part of convincing the verifier to accept. And the proof of that is just simply by this useful fact that we had before, right? Thinking of the jointly distributed random variables for the x is just going to be the choice of q1 up to qi star, and then kind of the rest of the random process is in the y. We know that with good probability over the choice of x, the residual probability over the y's, the conditional probability over the y's is still good. And this is exactly the reason for the loss of kind of 2 here and 2 here. Questions so far? Okay. And now I want to use this forking lemma. And forking is somehow, you can think of it as though we broke this kind of epsilon or epsilon over 2 probability that we had. We kind of split it into 2 parts. Good probability over the first I queries, that the residual probability is good. Okay, so I want to use, now with this analysis in hand, I want to use the Fiat-Shamir cheating prover to cheat in the original interactive argument. Right, so I want to produce an alpha, so with good probability over beta, I produce a gamma that makes the verifier accept. And I want to describe what is the cheating strategy. So here it goes. So I'm defining what P star does. So it essentially starts running the cheating prover for Fiat-Shamir. And it runs it whenever the Fiat-Shamir prover asks for a query to the random oracle. I'm just going to generate a fresh random answer and provide that. And I've assumed it doesn't ask the same query twice, so I don't need to worry about repetitions. So I'm just providing it with random answers, as you would expect from a random oracle, up to the I star query. I continue until it hits the I star query. I'm not going to answer the I star query yet. Okay, but I have in my hand all these queries. And I'm going to define alpha to be this query that the prover just made, and I'm going to send this particular alpha to the verifier. Okay, so again, I've started simulating the prover. I'm waiting until the I star query. Once I get it, I send that over as my message alpha to the verifier. Now the verifier tosses his coins and sends over a beta, and the answer that I'm going to provide to my Fiat-Shamir prover as an answer to the I star query is going to be beta. So I do that, and then I continue where any additional queries that the Fiat-Shamir prover might make, I answer with kind of fresh random coin tosses. Okay, good. So I kept running the Fiat-Shamir prover. Eventually, hopefully, it will output a message that it was supposed to output to make the Fiat-Shamir verifier accept. So some alpha prime, beta prime, gamma prime. I check for good measure, I check that the alpha prime that it produced is equal to alpha, that the beta prime that it produced is equal to beta, and then I look at the gamma prime that it sent, and I'm going to send that as my last message in the protocol. So let me just quickly recap what we did. So I, as a cheating prover for the interactive protocol, I'm running the Fiat-Shamir prover up to query I star, where I've answered everything with just kind of random responses. For the I star query, I don't want to answer yet, because I'm sending the I star query to the verifier. The verifier responds with the beta. I'm going to use this beta as the answer to the I star query, then continue the interaction with random answers. Eventually, I get back, the Fiat-Shamir message, and I send over gamma. Any questions? Okay, so let's see. We'll try to see why this works. Okay. So unsurprisingly, we're going to rely on the forking lemma. And what we get, maybe I'll go back to the description of the protocol. What the forking lemma tells us, because we've kind of emulated all of the answers to the random oracle using fresh random coin tosses, we know by the forking lemma that with good probability over this phase, we still have kind of relatively good probability over the rest of the interaction for the verifier to win. So kind of stating it more precisely, with probability epsilon over 2t over the choices of q1 up to qi star, sorry, this should be I star over here. The forking lemma tells us that with probability, another probability epsilon over 2t over the remaining coin tosses, the Fiat-Shamir prover is going to win, and win meaning make the verifier accept, and it's going to do that with the message. We had this condition that the qi star is equal to alpha. So the alpha prime that it's going to generate is equal to the same alpha that we have. That means, so we have epsilon over 2t probability of this event happening over the qi's, and another epsilon over 2t probability over the remaining coin tosses. So overall, we have epsilon over 2t squared, probability of our interactive prover P star winning in the original protocol. Remember that we said that kind of epsilon is noticeable and T is polynomial. So overall, we have kind of inverse polynomial probability of success, which is non-negligible and therefore a contradiction. And you also see here kind of this epsilon over T is where we really need kind of negligible probability. We couldn't have lived if our if we only had like a constant soundness. Okay, so far, so that was again the analysis of soundness of Fiat-Shamir in the random oracle model. Now, what about zero knowledge? So, and it's somehow simpler and more complicated simultaneously. So we haven't really defined what zero knowledge means in the random oracle model. There are actually multiple different variants, and I don't want to get into it. But just in the level of intuition, what happens after we compile with Fiat-Shamir? So, what is the view of the verifier? So the verifier sees alpha, beta, and gamma. That's the message that gets sent. But it also kind of has oracle access to some random function such that R of, if you hash alpha, you get beta. And, how can you simulate having access to a random function? Seems kind of weird. You need to make up a definition to be consistent with that. That's what I didn't want to do. But it certainly doesn't seem like there's any kind of gross violation of zero knowledge. And, right, so can a verifier obtain such a function by itself? Well, unclear. Long answer is that depends on the definition. I don't want to leave you hanging, so later we're going to get back to this point in a couple of slides. We're going to get back to this point and give you kind of a better explanation of why you shouldn't worry about zero knowledge when applying Fiat-Shamir. Okay. Sorry?
In your transformation, the input to random oracle is both x and alpha, but in the proof you only use the alphas.
Right, so somehow people tend to throw in x for good measure. It's crucial if you want to talk about adaptive soundness. I believe, but if not verified, although the proof seems to give it, that if you don't care about adaptive soundness, then it's enough to hash alpha. Okay. Probably because you want adaptive soundness there, because you want to reuse. Yeah. Okay. So the conclusion so far is that Fiat-Shamir is sound in the random oracle model and zero knowledge under suitable definitions. But we have this kind of fictitious model of the random oracle. In real life, we don't have access to this huge table of an exponential exponential number of random bits. If you're thinking about using something like a pseudorandom function, forget about it. It doesn't work because you need to kind of, it's not going to look pseudorandom to anyone having the description of the PRF. So we can't just use or assume that we have hash functions that are random in this way. And this kind of motivates the question, you know, are there any concrete hash functions for which we can use to make Fiat-Shamir secure? So kind of Fiat-Shamir passed this first sanity check, but what about using an actual hash function? You know, what about using AES? And now I have a little bit of bad news to share. So turns out, and the bad news is going to get even worse in a little bit, but turns out the result of Canetti, Levy, and Goldreich shows that there exist protocols that are secure in the random oracle model, but if you take any instantiation of the random oracle, meaning replace the random oracle by AES or any hash function that you like, the protocol that you get is totally broken. Okay, so this is kind of a negative indication. You can interpret this as a negative indication of what soundness in the random oracle model means. And indeed, now, you know, I promised a couple of slides ago that I want to discuss what security in the random oracle model means, so let's do that now. So I'm going to kind of give two different views. I'll tell you later what I think among them. So kind of the optimist version is, you know, the counterexamples that we have, such as the Canetti, Halevi, Goldreich, and others that I'll talk about soon, these counterexamples are contrived. These are not natural protocols like, you know, identification schemes that we use, Schnorr or Komato or so forth. They were kind of specifically designed to be insecure when compiled with Fiat-Shamir. And the random oracle model analysis that we have gives a strong indication that Fiat-Shamir will be secure for kind of natural protocols. This, again, the optimist view. And, you know, you can just take this as a good heuristic. And this heuristic has shown itself to be incredibly useful, both in terms of feasibility results, getting things that we don't know or even don't know how to do in other ways, let's say, or we have like very strong assumptions if we want to do them otherwise, or getting like kind of huge efficiency boosts. So this is kind of reasons why we would like to kind of to be convinced that the random oracle analysis tells us that that instantiations should be secure. On the other hand, we have, you know, the eternal pessimist, which say, you know, basing security on an assumption that A, we don't understand, and B, we have counterexamples for contrived as they may be. This is kind of something that's highly undesirable and can be dangerous. We don't know if and when the counterexamples, the contrived counterexamples, will turn into actual counterexamples. So there are two different views, I think, in the community. I personally lie somewhere in between. I do buy that it's an interesting heuristic and certainly helps in terms of feasibility and efficiency. I also think that it is quite dangerous to use something that we don't understand so well. But this is kind of, I feel, is a matter of personal choice, so I'll leave it up to you. But I think it's important to know that there are kind of different views in the community. Okay, so so far we've kind of started understanding how Fiat-Shamir works when using a random oracle. I want to start talking a little bit about instantiating the Fiat-Shamir transform using an explicit hash function, despite, you know, negative indications that I've said, and I'll go into more detail in my afternoon talk. Okay, so I think this is a really basic and important question in cryptography. Can we instantiate the Fiat-Shamir transform securely using an explicit family of hash functions rather than, you know, this random oracle model? And let's be a little bit more precise. So I'm going to say that a hash function family H, so just a family of hash functions, is Fiat-Shamir compatible for a particular protocol pi if you take the protocol pi, compile it using the Fiat-Shamir transform, and using this hash family H, you get something that's secure, meaning both sound and zero knowledge. Just to be explicit about what I mean by using a hash family, so the idea is that the verifier chooses a random function from the hash family, sends over a description of this hash function to the prover. The prover, as before, hashes alpha and possibly also the input x, gets beta, and sends over alpha, beta, and gamma to the verifier. And we say that the hash function h is Fiat-Shamir compatible for this protocol, for the original protocol, alpha, beta, gamma, if this thing is, the resulting thing is sound and zero knowledge. So before talking about soundness, I want to talk a little bit about zero knowledge, and also kind of going back to this point, this annoying point that we had with analysis of zero knowledge in the random oracle model. I want to show you that actually arguing soundness when talking about a concrete hash function family becomes much easier. You don't need to worry about kind of different definitions and so forth. So the basic requirement that we'll need in order to argue zero knowledge when using an explicit hash function family is something called programmability, so I'm going to say that a hash function family is programmable if it's possible to sample a random hash function from the family conditioned on, you have some like particular alphas, alpha and beta that you care about, and you want to sample from the conditional space of all h's, all little h's, such that h of x alpha is equal to beta. Okay, so you can sample this kind of conditional hash functions. And I want to argue that if our hash function family h is programmable and our original protocol need only be honest verifier zero knowledge. Alon, did you define honest verifier? Alon left. Did Alon define honest verifier zero knowledge? So zero knowledge only needs to hold with respect to the behavior of the honest verifier. As long as you have that, then you get that the compiled protocol, this should be capital H, is zero knowledge, which means that if we look at the kind of random oracle analysis that kind of told us something about soundness in the random oracle model, and then instantiated it with a concrete hash function family that's programmable, then we get kind of standard zero knowledge. Okay? So how do we prove this? We want to prove that the resulting protocol is zero knowledge, so let's construct a simulator. So this is a simulator for the compiled protocol. So what does it do? First of all, it kind of sorry, it's missing some text. So it generates alpha, beta, and gamma based on the honest verifier, the simulator that exists for the original protocol, based on the honest verifier zero knowledge property. Right? So this simulator generates a view that's computationally indistinguishable from the view of the honest verifier. And we're going to call that alpha, beta, and gamma. Now I'm going to use the programmability to sample the again a typo. I want to sample little h conditioned on little h of alpha being equal to beta. I can do this based on programmability. And then I output little h, comma, this transcript, alpha, beta, gamma. And an exercise I'm going to give you a hint is to show that these distributions are, so they're identical if we start off with perfect honest verifier zero knowledge, otherwise they're computationally indistinguishable. And the reason is that basically the difference is that over here we sampled alpha, beta, gamma, and then sampled h conditioned on alpha going to beta. In the actual interaction, we're sampling h at random, but then sampling kind of beta as h of alpha. And you can convince yourself that these two experiments are the same. Okay, in general, if you have like two random variables, two jointly distributed random variables, sampling x and then y condition on x is the same as sampling y and then x condition on y.
So it's not only the programmability is not only that you can find such an h, but also that you can sample such an h at random.
Indeed. So you want to sample from the distribution of all h's conditions. So this is a conditional probability statement, not just find a particular h. Okay, so this was kind of zero knowledge when using a concrete hash function family. Now the trickier part is about soundness. And I already mentioned this result of Canetti-Levy-Goldreich, that there exist protocols that are secure in the random oracle model, but are insecure when actually instantiating the random oracle model. Turns out the situation is even worse. So a result by Barak that Alon will talk about in the next lecture, and followed by Goldwasser and Kalai, shows that there actually exist kind of interactive arguments that are sound, but if you compile them using Fiat-Shamir, with a concrete hash function family, you're going to get a protocol that's not sound. Okay, so really very strong and negative indication that Fiat-Shamir is not sound when using a concrete hash function family, which is somewhat unfortunate. So kind of a glimmer of hope that we're going to talk about in more detail in the afternoon session is that the counterexamples that we have actually turn out to be interactive arguments, meaning they only satisfy computational soundness, only soundness against efficient cheating strategies. And one could hope that Fiat-Shamir Transform is sound if what you start off with is an interactive proof, meaning that it has soundness against all cheating provers. Okay, if we don't have a negative indication, then why not hope? So why not hope? So because there's a reason. A result of Bitansky et al. Shows, actually two different results of Bitansky et al., this was a merge of two papers, shows that it seems very unlikely that we'll be able to show that Fiat-Shamir works even when starting off with an interactive proof. They show that there's something, we haven't talked about this in detail, but to people who know about this in the audience, kind of standard techniques that we have should not be able to work generically to show that Fiat-Shamir works for proofs. Okay, which is, again, a very bad indication. And I think for a while there was a lot of pessimism in the theory community about actually instantiating Fiat-Shamir in any setting. And we're going to see that this has recently changed. We're going to talk about it in the afternoon session. I also wanted to mention, and I'll talk about this again more in the afternoon session, that this question of instantiating Fiat-Shamir for proofs is closely related, even equivalent, to the question of whether if you take a zero-knowledge proof rather than an argument and repeat it in parallel, does it preserve zero knowledge? And this was also open for a while, and we understand it better now. And again, I'll talk about it more in the afternoon session. So I'll stop here.